about resource analysis. And so before we start, there will be two logistical problems. So the first problem will be that I will write too small. So there's one person in the back, maybe at the very left. What's your name? Allison. So Allison, your responsibility will be if I write too small, then you have to scream larger, and then I will adjust it. And also, yeah, if I'm not loud enough, also say something. Okay. Another thing I wanted to mention is, but I think Ankush is not here. So there is one of my PhD students is here, Ankush Das, and he just took a course on this topic at CMU, but I think he's not here right now. But he will hopefully be around later in the afternoon hands-on session or whatever this is called. And can help you with the problem sets. So there will be every day there will be a problem set, and this will be on the Piazza resources page. So the first one should already be up there. I uploaded it this morning. Okay. So yeah, resource analysis. So our goal, or one of our goals in PL, is to make it easy. Make it easy to write good programs. So, and the question is, what is a good program? What's a good program? Yeah, Allison, is that okay? So, yeah, what's a good program? What properties does a good program have? Anybody? Yeah.
It does what we want it to do, and fast.
Yes, so it's correct, and it makes use of resources efficiently.
I have another.
Yeah, there's another one.
I have another definition.
Yeah.
It does 99% of things, and it's fast to write.
It's fast to write. Yeah, that's also another thing that's important. Yeah, and yeah.
Is it read?
Yes, exactly. It's easy to read, to maintain. So there are like a lot of things that are important, but one of them is making efficient use of resources. So, and you can even say that like this is part of being correct or like part of the correctness of a program. So if you think of a program that runs out of stack space, I mean that's certainly not like a correct program that you can ship to a customer. And also like if it takes 100 years till you get a result, that's probably also not a really correct program. So. Yeah, resource usage also is related to correctness when you have a program in the real world. So the next question is, so what are resources?
Yes.
Yeah, disk space. Okay, disk space. Then I heard time, right? Yeah, memory.
Network.
Yes, network bandwidth. Also like the amount of data that's sent over network, for instance, important when you have like mobile devices. And yeah, the list continues. So I mean, there's also like sometimes money as a resource. Yeah, if you think of something like AWS, yeah, so they have, for instance, this Dynamo DB where they charge you on the number of queries. So yeah, then the money might also be like a resource that you're interested in. Oh yeah, one thing we forgot that's also very important now is energy usage. This is of course related to time, but still a bit different. Again, like on a phone, it might be very expensive to send data over the radio, so it's not always tied to the CPU usage. Okay, good. So our goal is it here to determine the worst case. So that's what we focus on today. Resource usage of a program. And what we're going to do is we're going to do that as an easily understood function of the inputs. So easily understood function, what does it mean? Well, it's a bit undefined, but for instance, what it means is like if you give me inputs of the program, then this function should kind of like be computable immediately. I mean, you could also kind of like instrument the original program with a counter or whatever, and then you could say this is the answer to this question. But that's not what we're interested in. We want to like summarize the behavior in terms that are easily understandable for the user. How is that done today? So resource analysis today. How do people analyze their programs?
By hand.
Yes, by hand. And so when they do that by hand, they often don't even analyze the programs, right? So it's more like analysis of algorithms. So analysis of algorithms. So, and there, what people usually use is this big O notation, so asymptotic, and recurrence relations. Yeah, I think that's something that all of you learned in your intro courses. Yeah, but to do it that way has many problems. So anybody, what are problems to analyze programs like that? Yes, so you don't get precise information. So why is that a problem?
Because when you want to choose between like implementation.
Exactly. So if you have, for instance, two implementations of the same thing that have the same asymptotic behavior, how do you know what's better? And then they usually have these hand-waving arguments, and they say like, oh, the hidden constants in the big O of this other one are better, but it's really not part of the analysis. It's more like hand-waving. So yeah, that's one thing. Another thing is that you even can't be sure that the program you implemented is really an implementation of the algorithm that you analyze, because usually what they do is they have the algorithms in pseudocode, right? And it has no semantics, so it's not even clear how that relates to your program. And of course that it's not an academic problem, because so if you have like a bug or something like that in your code, the resource behavior might be much worse, like a resource bug or performance bug they call it. Other problems with this. What else do I have written down? Yes, so another big problem is when you're interested in small inputs, which is kind of like always the case, right? So because yeah, often, like for instance, your input is an integer, and so it's a small number anyway. So this kind of like big O is maybe not appropriate for all cases. Okay, there's another thing that people do apart from this. Yes.
For specific execution tasks like profiling a program.
Exactly, testing. So that's the other way. So testing is good because it gives you concrete information for specific hardware, but it also has problems because you can only test so many inputs, and you can never be sure you really found like the worst case behavior, and you can also often not see how it works for large inputs because it's not feasible maybe to test it. Okay, so yeah, so what I work on and what I hope what will be the future is that we use programming language technologies. So to do this, future PL techniques. So and the idea, I mean, you've seen already a little bit about this. So you start with not an algorithm. You start with a program. Okay, so start with a program, not an algorithm. And the advantage is that, like, the program is the stuff you can execute, and you actually work on the code that will run on the machine. And another advantage is that the program has a semantics, so you can argue exactly about what it's doing. And of course, so we want to define what is the cost of the program, so we use a cost semantics. This is another problem when you look at the this analysis of algorithms that they do. That sometimes it's very unclear what the cost of an operation there is, and then it's also like always a question, how is it implemented and so on. And here we kind of like fix what the cost is in a mathematical model, and then so you've seen already a little bit, and I'll come back to that in the next lecture. And show you how it works for resources like memory too. So this is something you're going to see. And the main part of these lectures is about providing tools. To help analyzing programs. So, and that, can be automation, specification, and, composition. And certification. Yeah, so automation is kind of like you write a program and then like it's automatically or semi-automatically analyzed for you, and there's like then you get a formula that describes the resource usage. And specification is kind of like that you have a way even in a formal way to write down what the resource consumption of your program will be. Now you see it's like this big O notation, but it would be nice to have like the resource cost of a function maybe given in its type and not like in a separate comment. So another thing is composition. So if you have two programs and you have the cost, how do you get the cost of the whole program, which is not trivial in many cases. Okay, and certification is like if you have computed or if you have a bound, how can you prove that this is a correct bound, and how can you certify it with a certificate that you can ship with a program and that somebody else can check easily. So these are the things we're going to look into. And well, there's another thing that you can do here that I'm not going to talk about is how you can relate a high-level cost semantics to the actual hardware. So this is something that Bob Harper and Guy Belloc worked on recently, where they there's a paper called cache efficient algorithms, where they do such a thing where they kind of like say, okay, this high-level model relates to the hardware in an exact way. Good. So the first thing I want to do today is talk about the potential method of amortized analysis, because this is what we're going to use later to reason about the cost. I assume that most of you have seen this, so who knows the amortized analysis and the potential method? Yeah, not everybody, good, yeah. As usual, half. Yeah, but that doesn't matter. So yeah, what is the potential method? So it is a way basically to get good worst case bounds for a sequence of operations. So amortized analysis. So this has nothing to do with programming languages. So this was done by the theory people, by Tarjan and Slater, to analyze data structures and algorithms. Okay, so and specifically, there are different versions of it. So we're gonna use the potential method of it. So and the goal is here to get good bounds on sequence of operations. Yeah, and worst case bounds. So sometimes people ask me, isn't this like amortized analysis kind of like an average case analysis? But that's not the case. It's really for worst case. And the trick that it does is that you have a situation where you have operations that depend on the state, and sometimes operations are very expensive and sometimes they're very cheap. So now you want to analyze a sequence of operations, and if you would do it in a naive way, then you would for each operation assume the worst case, and then just multiply the worst case by n, because you have n number of operations, and then you would get a bound that is very loose, because the worst case cannot appear in every operation. It kind of like amortizes over time usually. Okay, you'll see an example later. So the idea is to introduce the potential function. So idea introduce potential function phi that maps a program state to a non-negative number. So here I use rational numbers, but it doesn't really matter. So that's basically what we're going to have in the type system later. Because, yeah, we're going to do it like in the type system that you'll see in the next lecture, hopefully. Yeah, we're going to like formalize this idea in a programming language. So, and now you have given operations, given that, yeah, I call them O, that operate on this program state and that have some cost. And the idea is now when you analyze a sequence of these operations and then you take into account this potential to pay for the cost of the operation. So we say the amortized cost of an operation, the amortized cost of our operation O is so, and the first thing we do is we abstract over the state. So take the maximum over all program states, and so we take the real cost of the operation. Yeah, let me just write it like that. Plus the potential after the operation minus the potential before the operation. So, and the idea is that you use this potential kind of like as a buffer to pay for the expensive operations. So when the cost is high here, what you want is that the potential at this state is also high. So that kind of like the cost in the example we're going to see, the amortized cost, well, I don't want to spoil it because I want to ask you later, is kind of like more even over the operations than the actual cost, which can vary a lot. Okay, so but what you also have to take into account is the potential at the next state. So when you have a costly operation, then you also want to have a low potential at the next state. So otherwise it doesn't work. So you want to kind of like when you have high cost, you want to use up the potential to pay for it. So this is the idea. And then well, why do we do it like that? So we have a theorem that says like, okay, given given starting state as 0 and sequence of operations O1 to On. And then what we want to know is, okay, what is the total cost of the operations? Well, yeah, I have a bit of a sloppy notation here, so yeah, so SI is kind of like the state after I operations have been executed.
Yeah. We can have the same operation cost more or less depending on state at different points.
Yes.
So do we split for the analysis here because we took the maximum cost
Yeah.
of the operation 4 times. right? So will we split the same operation when it's costly and less costly?
No. We
For
will,
example, a dynamic array, right? We have a enlarging and the regularization, right? So in this case, it would still give us its own value.
yes, so in this case, that's exactly a good example for the amortized analysis. There, the amortized cost will be constant. Yeah.
Oh, so, yeah.
Okay, because like that's why you have this potential here to kind of like even that out. This cost here will not be a constant. Okay. So, and we can bound that by the amortized cost. Well, actually, I don't have to. Oh, maybe it's okay. Could be different operations, right? So there might be different operations in the data structure, so the OI might not be the same operation all the time. So that's why I write it like that. Plus the potential at the starting state. So the idea is that when we, and you'll see that in an example in a second, when we want to bound the actual cost of our sequence, then we just sum up the amortized costs, and we take the potential at the initial state, which is much easier to compute in some cases, or much easier to calculate, as you will see in a moment. Okay, and to prove that, I mean, you can try that this afternoon. It's not hard. I'm not going to do it here. It's just like how we call it in German, telescope sum. That's the same in English. Yeah. So most of the terms cancel out, and it's not hard to calculate. You'll be able to do that. Okay, let's see how that works with an example. Yeah, there are questions so far? Yes.
You have the sequence of states and
Yes. So I didn't say that. So Si is the state after after executing O1. Oh, did we start with O1? Yes. Yeah, so you start with S0, then you get S1 and so on. It's no, the operation on this particular state, yeah. So the notation is not great, but yeah.
Okay.
So maybe it's better to write it with a comma in the middle. Yeah, cost of O on the state, yeah. Yes. Well, it's kind of like, you'll see it in a moment. It's kind of like evening out the cost of the operation. So it'll become more clear when you see an example. So you have these operations here that you execute. Maybe it's just one operation, and sometimes the cost of the operation is high. Yeah, for instance, we had this example where you use an array to implement a set or something. Where you sometimes when the array is full, you have to double it. Okay, so then you say like, okay, inserting something in this data structure is very expensive because the worst case is it's linear in the cost of what you already have. And then you say like, okay, so if I want to insert n things, then I have like a quadratic cost. But this is of course not true, because you will only have this linear cost after it filled up, so it kind of like it averages out over time. It gets amortized. And so to analyze this mathematically, you introduce this potential function, and that will help you to argue in this case, for instance, that like inserting something has a constant amortized cost, so the cost of inserting n things is kind of like linear, not quadratic.
So on the left, do we start using the states at I or at I minus 1? So does operation 1 apply to state 0 or to state 1?
To state 0.
To state 0.
Yeah.
Is it state 1 right now?
Uh,
we say cost OISI. Is that SI or SI?
oh yeah, that must be 0, right? Yeah, good point.
So now we have operation 0.
Oh no, it was correct before. Because we started with operation 1, but on state 0.
Technically, the starting state is S1.
No, I think it has to be S I minus 1. Yeah. Okay. Good. Oh.
But we're talking still about worst case analysis and not about average case analysis, even if things average out about that.
Exactly, and that's an important point. It still gives you in the end, and that's what you see here. The cost here is kind of like the worst case cost of the operation, so you still get a bound on the worst case. Okay, good. Yeah, or like, I mean, the cost here doesn't have to be the worst case. It can also be the exact cost, but still, what you get is an upper bound in the end on it. Yeah. Okay. Good, so let's do an example. So in the example is a binary counter. So this is our state, B, which has a finite number of bits, k, to be 0. Yeah, it's not really important where the higher value bits are, but let's say these are like it's usually, so these are like the high, and this is kind of like the lower ones. Okay, and important is that the thing has a fixed size, so there will always be k bits, and then like it'll overflow. So yeah, that's our state. And our operation, we only have one operation here. Increment the binary counter, do +1. And our cost, so I use the sheet here. So, the cost of an increment is the number of bits flipped by the operation. Yeah, so for example, so if you have increment of 0, let's say 1, 0, 1, 1. So then, like, yeah, the answer of that is 1, 1, 0, 0, and the cost is 3. So, and now what we look at is a sequence of n increments. So now consider n, let's write it like this, inc operations, and what is the worst case cost? So what is the worst case cost of one operation to start with? Log n? Well, how many flips? I mean, our cost function is the number of bits that need to be flipped, right? Yes. O of n, yeah, that's right. But we can be more precise even. So n plus 1, k plus 1, yeah, we can be even better. So how many, if you look at it, how many zeros are flipped by an increment operation? 1, exactly. So, and how many ones are flipped? Yeah, the overflow case, but at most 1 is flipped. Yeah.
The number of 1 bits starting from the right with no intervening zero.
Exactly. So in the worst case,
That's all of it.
exactly. So in the worst case, we have observation. So the cost of the increment b is, well, the number of ones plus 1 for the 0. In the worst case. Oh. Okay. That's already good. So let's come back to our n increment operations. So what's the cost there? Is it, so I mean, if we would just say n times this, then it would become like something quadratic. But that's not really the case. So we use the potential method and define a potential function. So that's always the creative thing you have to come up with. And anybody has a candidate for a potential function? So the potential function always has to have a lot of potential when the cost is high, right? And then afterwards, it has to have a low potential after you did like a costly operation. So when is an operation going to be costly? Exactly. When we. Yes. So exactly. So the cost is high when we have a lot of ones. So, and we need a potential function that is high when the cost is going to be high. So what we're going to try is we use the potential function number of ones. Okay, and now let us determine the amortized cost. So now we're basically done with the creative part. Now it's just like mechanic computation. So let's say the cost. Well, let's first say we fix one concrete B, and now we define the cost of our increment of the B is T. Okay, so that means we have T minus 1 flips from 1 to 0, and one flip, well, if we don't have the overflow case. Oh no. Oh, that's a good point. Well, we have to think about the overflow later. One flip from 0 to 1. Well, unless we overflow. So in this case, we have to think about it together because I didn't consider that. So, okay, and now we want to compute the amortized cost, and I was trying to be clever and write it somewhere. But it's below? Ah, yeah, exactly. So let's look at this expression here on the right under the max. So there we have the cost of the increment of B plus the potential afterwards minus the potential at B. So, and this we just said we call this T, okay, and then here we have we just put in the definition of the potential, so we have the number of ones in the counter after the flip, and here the potential of B is just the number of ones in B. Okay, so but now we can express this number here basically by saying like, okay, this is the same thing as B, okay, minus the number of ones we flipped, T minus 1, plus the number of zeros we flipped, 1, which is not always the case if we overflow. We have to come back to that later. Minus our potential of the B. We don't change that. So there's something wrong with the parenthesis. No. So exactly, it's 2. And that's what I wanted. So, yeah, so as a result, the amortized cost of our increment is 2. So and then the total cost of our sequence of operations. So total cost of n increments is smaller than 2 times n plus the number of ones in the, let me write it like this because I don't want to write it lowercase, where this is kind of like the counter at the start. Okay, so the cost is not quadratic, but linear in the number of increments. And we have a nice proof of that. So what you will see is that you have a similar situation when you reason about the cost of programs, actually. So where you kind of, at each operation, you just want to take care of the constant cost. That's a very way to think about it, and the rest is going to be handled magically by the potential. So we're going to have the same thing later on in the type system that you're going to see. Okay, questions? It only has to be non-negative. That's it.
I mean, like for algorithm analysis in general, the sign have some relationship with the cost, so that actually gives you the amortized cost?
I don't think so. I mean, it's just like, we.
Just make something up, right?
Yeah. Well, no. I mean, you can. Then you just get like this amortized cost. Then, if you have like a bad potential function, then it does not, help you in the analysis because, if we would say like our potential is a number of zeros in the bit string, then we wouldn't get our nice bound here because the amortized cost would not be constant, but would be what probably would be linear in this case. Yeah. So the thing is, you have to be clever with picking the right potential function. Otherwise, you don't get a good bound. Yes.
So, piggybacking off that, is there a way to know if we have the best bound?
I'm not aware of any way of knowing that. Yeah, that's a good question. I don't know. Yeah. Yeah. I think. He kind of like uses the potential method to reason about cost, but originally this was done by Tarjan. So a good place to start reading about it is just like standard algorithms and data structure books. But Okazaki is also a great place to read about it. Yeah. Yeah.
So if inc was not a best function from a binary counter to a binary counter, but to something else, would we have to unify the input and the output of the function to be able to call both states? You know what I mean?
Yes. So probably would have to do that. Yeah. It's a.
But it means that the binary counter is the state.
Yeah. So that's usually a bit unclear when they do this analysis what the state is. So it really depends on your application. But this is something. This is kind of like an informal analysis, so you can make it up. You can kind of like define what the state should be.
But then I need to take all the types in my program and unify them and represent them in one way.
Oh yeah. Well, yeah, sure. We talk about programs later. So then you will see how we do it in the type system. It will be a bit different from that. This is just kind of like informal to just get the idea of how this like amortized analysis works. So in the type system, it will be a bit different, you'll see. Yeah. Okay, good. So then we can start with the PL stuff. And let me continue here. So the first thing I want to introduce is first order functional programs. So we're going to define the type system only for a very simple language. So maybe, well, so this is a new chapter. Forgot to number them. First order functional programs. So why do we do it for first order programs and not something like the lambda calculus? Well, the main reason is I don't want to deal with function closures in these lectures. So function closures for cost analysis are particularly challenging. So you can have effects like, you know, say like you have append, and append is a function that has like a cost that's linear on the first argument, okay? So if you apply append to the first argument and you call the result function f, yeah, then you have a function f that has a linear cost, but the cost is not linear in the argument, which is the second argument of append, but in the data that's in the closure. And that creates a lot of trouble. There's research on that, and there are like some solutions, but I just don't want to get into that mess. So that's why we focus on first order programs. So we have a syntax where we have variables. So then we have function applications. So you already see the functions are treated different from variables. So here's a concrete syntax. So then we have true and false. So we have booleans. We have an if statement. And another thing here that I want to point out is we have programs here in what I call a share-let normal form. So sometimes this let normal form is called a normal form. And there the special thing is that you don't have an expression here at this position of the if, but you have a variable. Okay? And you can always bring programs in this form by using let that I skipped here. That is the only construct in the language that allows you to have sequencing of expressions. So that's the only point you do that, and this is good enough. So the let is, the concrete syntax is let x equals c1 and e2. Yeah, and the if is also clear. If x then e1 else e2. And yeah, so that I think this notation you have seen before, right? With the like bindings. Did they introduce that? Yeah. So the x gets bound here in the e2. So what we also have are pairs. So so we can have functions with multiple arguments by using our pairs. There. Oh. Pair. And we have pattern match for pairs. so we also have lists. So we have nil, and we have pattern match on lists. So again, we have our share-let normal form, so we match on X. If it's nil, it's E1. Otherwise, we get a head and a tail. Go to E2. Oh, I forgot about the cons. And so then another particular thing we have is a sharing construct. So this is something you have to use every time you want to use a variable multiple times. So you're going to see we have like a particular type discipline. It's called like an affine type system, and this allows you to use every variable at most once. So if you want to write a program, so that's it, by the way. Oh yeah, let me, otherwise I forget, tell you how that looks as a concrete syntax. So it says let share x as x1, x2 in E. So in an E, you can only use this like x1 and x2. So yeah, so that's it with the syntax. So if you want to write a program, for instance, let's say let x equals true in x, so we're going to forbid that later on. So you can't write that. The type system will make sure that this program is not well typed. What you have to do instead, you have to say, okay, let x equals true in share x as x1 and x2 in x1, x2. And so the reason we do that is because we use this potential method, and there will be some potential associated with x, okay? And you want to control what happens to this potential, and you do that through this sharing. Yeah, so you basically want to say you cannot use the potential twice. So you have to kind of like split it up, and this is kind of like the expression of that in the syntax. So you'll see how that looks in a moment. Okay, so before I'll come to that, I want to talk about something else. Oh yeah, I should mention another thing. So I mean, you have this weird sharing, and yeah, let me maybe first write that down. So expressions are in expressions are in share-let normal form. Okay, so that means that like, yeah, you have at, oh here, there's a comma missing. Yeah, that you have at all positions where it's possible, you only have variables instead of full expressions. So,
Sorry, quick question.
Yeah.
So the construct below the nil, what's the?
Oh, that's a pattern matching.
Okay, and how does it work?
So this is match x with nil E1 and with x1, x2, it's E2. Okay, so first of all, you can take any program that doesn't have this restriction. So where you, for instance, here have in the match full expression, you can transform that into an equivalent program in this share-let normal form. Okay, so this is like also like an exercise that you can do. You can implement that, and yeah, you can do this like program transformation. It's yeah, not that difficult. It's not so easy to prove that it does the same thing, but it's pretty clear that it does. So that's a well-known fact. Good. And the other thing I have to say is, okay, where do these functions f come from here? Okay, because they are different from the variables, and you see there are no lambdas in the language, so you need a way to introduce them. So a program, yeah, and I define what that is more formally. Program is simply a list where you say, okay, you have a function, and then you have the function body that only has the y1 as a free variable. Okay, and you have a list, let's say n of those. Okay, and they are mutually recursive. So you can use all of these functions that you're defining, you can use them in the EFIs. Yeah, that clear? Okay, good. That's just a function name. So every function comes like with a pair of a variable that's the argument and expression EF. Yeah, but I'll define it formally in a second. But I'll do it after I define what the types are. Okay, so now we define an affine type system, and so affine means that you can use variables at most once. You don't have to use them, otherwise it would be a linear type system, yeah, when you have to use them exactly once. But you can only use them once. That's why it's affine. So what I call data types. So data types are types without arrows in them. So they are, for our simple language, either booleans or lists or pairs. Yeah, so this weird notation here is just what I like to use for lists. Okay, and then we also have function types. Oops. Should speed up a bit. What's wrong? So function types map these like zero order types to zero order types, or data types to data types. So they can't be higher order. And in our type system, we're gonna have function signatures, sigma, that map function IDs, function names, to function types. Okay, and a type judgment has a form sigma, gamma, expression E as type. So that says, like, given the function signature sigma in the context gamma, the expression E has type T. Yeah. So context, didn't say that. Text gamma, they map variable IDs to data types. Okay. So oops. So, and both of these things are always finite mappings. And we have a finite number of functions and a finite number of variables. So definition, so a well-typed, and we're going to talk about the type rules in a moment. Well-typed first order program consists of signature sigma and a family, the function bodies EF and the variables YF for every F in the domain of sigma. Such that we have sigma and our gamma is ft1, t2 if sigma f equals t1 arrow t2. Okay, we didn't define what the type judgments are yet, but yeah, is it clear how that works? So you have this list of functions, right, with variables. So this is just here, this family, yeah, so this is what you have seen over there. Yeah, and now we say like, okay, every function body has to be well typed, yeah, by giving the right type T1 to the argument, then you have to get the type T2. Questions? Okay, good. So now we're gonna see, we're running out of time, but I started later, so I maybe still have 10 minutes. So we're gonna see some of the type rules. They are also on the problem set, on the first problem set. There's a full list. Okay, so that's an affine type system. So that means it's a bit different from the type rules you've seen before. So you always have in every type rule the same signature. So this will never change. So you could also kind of like leave that out and say you have a global one, or write that at some other place. So this will always be the same. So, and now we're going to see the rule for the variables. Okay, so the interesting thing here is this context gamma here. Okay, so you notice the difference to the rule for variables that you've seen before. So before there was like, you have like a context gamma here, and you have gamma of x is t. Okay, but here you say x is the only thing in our context. So you can't have anything else. You have to get rid of it before you get to this point in your type derivation. And another thing that's interesting is the function application rule. So so here you have a variable x type T1 in your context, and again that's the only thing you have in your context, and then you have the application of f to x, and the whole thing has type T2 if you have this function type in your signature. So let's look at the rule for let. So let me write it like that. So here what you do is you split up your context into two parts, gamma 1, gamma 2. Okay? And if I write something like that, it means that you kind of like really, as if you would like write it down on a piece of paper, you split it in the middle. Yeah, so the domain of the gamma 1 and gamma 2 has to be different. So there are different variables in both of them. Okay, so this is kind of like a notation that I use. And then what you have to do is you use the first part of the context, the gamma 1, to type the E1. And let me use the right name. Okay, you get T1. And then what you do is you take the same context, never changes, and you take the gamma 2 and you add the x to it with a T1, and you type the E2, and you get the final T. So, and here you see what happens. Yeah, you can use a variable only once. Okay, so in your gamma, let's say you have some x in here. Okay, then you have to decide when you do the split, do you put it into the gamma 1 or gamma 2? Okay, so if it's in the gamma 1, then you can only use the x in the E1, and if it's in the gamma 2, then you can only use the x in the E2. Well, it's unfortunate that this was called x, so let's say we talk about y. Okay, you have a y in the initial one. Okay. Questions so far? Okay. So another rule that's interesting is the rule for sharing. So here we have Gamma that contains the variable x, t prime, and then we want to share the x by using new names, x1, x2 in the E. So, and this is the only place where we can kind of like use something twice in our type system. So x1 gets the same type t prime because it's the same thing. x2 the same type t prime, and then we type our E and we get t. So yeah, so you haven't seen the semantics yet, but the only thing that will happen is that in your environment, you take the value of x and you put in the x1 and x2 with the same value. So it might look a bit strange to have this restriction with the sharing, because in the end it's no restriction, right? It allows you to use something as often as you want, but it gives us later in the type system one particular point where we can say what to do in such a case. So it's just for us like a convenience, a technical convenience to talk about that. It's not really a restriction on the programs, but it helps us to kind of like localize our efforts to one place. Okay, so the other rules are not that interesting, so maybe I'll show you the one here, because there's a space for Boolean constants. So there you just have to have an empty context. Okay. So far our rules are all syntax directed. Okay, that means we have for every construct in the language, every syntactic form, we have exactly one type rule. So we always know when to apply what rule. Yes, question?
Why do you not use split gamma for the pair constructor?
Oh, for the pair?
Yes.
Because there we don't have any. Yes, exactly. So let's write the rule. So for cons, let's say we could have x1, x2, L of t, yeah, and if I write something like that, it's kind of like the same thing as if you split contexts, right? So the domain of the gamma 1 has to be different from the domain of the gamma 2. So in this case, it just means the names are different. First, I will just have a trick to achieve that. Okay, so yeah, so you can look on the problem set so that they are all the rules, but I think this is kind of like the gist of it. I just want to mention one more rule that's kind of like different because it's not syntax directed. So there's one rule for every syntactic construct, yeah, but there's one rule that you can always apply. That's a so-called weakening rule. So if you read it top down, then you can say like, okay, you can always, add something to your derivation that is useless that you don't look at in your expression. Okay, and if you read it bottom up, then you can say, well, you can always throw variables away as you go up. Yeah. If you want to use a variable, then you have to always, and you're maybe in a larger context, then you always have to apply this weak rule until only the variable is left. Okay, so you can see that, for instance, also where this is needed in the rule for the conditional. Yeah, if you look at the rule of the conditional in the problem set, then you'll see you have the same gamma for the E1 and E2. And to make them equal, you sometimes have to use this weakened rule here. Okay, so that's all I want to do. Questions before we end here?
Why do you use an affine type system rather than a linear type system?
Because, that's a very good question. So, we're working on a paper where we use a linear type system. So here you're interested, later on we're interested in worst case problems, okay? And so, basically you want to be able to throw things away, and that's where this affine comes in. So you want to, let's say you have a conditional, okay? And in one branch you have a high cost, and another branch you have a low cost, okay? Then we just want to say okay, we have to have enough potential later on to pay for the high cost, and in the low cost branch we just want to throw it away, we don't care. And that's why you have the affine type system. If you have a linear type system, you get also something that's very interesting. We're working on a paper right now with that. Then you get a constant time. Then you get a proof of constant time, which is important for cryptography, where you don't want to have any leaks based on the time. More questions?
So is dropping that weakening rule enough to give you the linear type system, or do you have to make more modifications to the type system?
No, you just drop the weakening. Yeah. That's how I set it up. There's a question that's related to that on homework too.
So about this chair rule, so basically you take two variables, you do the third one, or you replace them?
No, you have, so here this x1 and x2, they get bound in E. So the free variables that you have here is x, okay? And then x becomes x1 and x2 inside E. So that's the way to read it. So basically you had a program that would use x twice inside the E, okay? So what you do is you rename it into x1 and x2, and then put the shared variable. So that's kind of like how you use it. Okay, good. So